So, in last class we have seen the success of Bohr model, but there are also failure of this Bohr model, means there are some things, some more things Bohr model cannot explain. Okay. So, this initially this hydrogen atom spectra, as I have shown you. So, let me tell you failure of Bohr model. So, according to Bohr model, what we have seen in hydrogen spectra, simple spectra. So, there are series like Lyman series, Bohr series, so and many others, right. So, in Bohr series we have given name of this line, red line, H alpha, H beta, H gamma, etc. Correct. When this spectra was observed in a powerful spectrometer with very high resolution, so then it was observed that H alpha line from where it is coming, H alpha line? It is coming transition between n equal to 2, n equal to 3, okay. From this, between these two lines, this transition, this give H alpha line, right. And then H beta, H gamma, etc. this from successive transition from n equal to 4 to n equal to 2, n equal to 5 to n equal to 2, etc. So, this H alpha line, this is in powerful spectrometers which is having very high resolution. There it is seen, it is observed that it is not a single line. It is composed of 5 lines. 1, 2, 3, 4, 5. It is composed of 5 lines. So, this is called fine structure of spectral lines, fine structure of spectral lines. So, what is the origin of these 5 lines? So, that means this all other lines whatever we are seeing in ordinary spectrometer, it is not a single line. Each and every line are having is composed of many lines. How many depends on? It depends, but in this case H alpha 1 it is composed of 5 lines. So, what is the origin of this origin of the fine structures of spectral lines? Spectral lines H alpha. Okay. So, that Bohr model cannot answer of this question. So, another fact is that this, you know, this alkali atom what is alkali atom? Lithium, sodium, potassium. Okay. Their valency is 1. Okay. Hydrogen atom also valency is 1. So, this alkali atom, their spectra is quite similar to the hydrogen spectra, is quite similar. Their spectra of alkali atom is quite similar to the hydrogen atom, hydrogen atom spectra, of course. So, means this hydrogen spectra have, it shows the series, defined series. This alkali atom also shows defined series. We will see later on, but it also shows different series. Okay. So, this from Bohr model, it was since their spectra have similarity. So, from Bohr model, it is possible, it may be possible to explain, and that was tried. So, this, because here in case of this atomic alkali spectra at alkali atom. So, this, as I told, this term value, then we write this R H Z square by n square, right, term value. And the spectral lines basically nu equal to difference between two term values. This is T n, generally we write T n. So, difference between two term value T n 1 and T n 2. Okay. So, it's R H Z square by n square. Okay. Now, this term value was adopted. So, these are for hydrogen like atom, this term value was adopted. Since this alkali atom is having more than 1 electron, this lithium is having 3 electrons, sodium is having 11 electron, right. So, but generally outer electron participate in the transition. So, difference between these many electron atom and 1 electron atom, that 1 electron, as I discussed in case of Moseley law. So, this for many electrons is outer electron, it's in that case this that positive charge Z, it is not fully active, okay, or this outer electron cannot see the full charge, positive charge, because it is screened by the other electrons. So, effective charge, positive charge will reduce. So, in that concept, so this for term value for this atomic spectra alkali atom, it can be written including one skinning constant like this, as I already discussed this skinning effect. Okay. So, that means this alkali atom, it has valency 1, means outer side electron only active, it is like hydrogen like atom. Okay. So, only correction we need for skinning effect. So, that if we introduce, so then this should be the term value for alkali atom. Okay. So, for hydrogen atom using this term value, so all spectral lines was explained. Okay. So, using similar seeing this similarity, so this Bohr model was adopted for this alkali atom, and it seems this should be the turn value for the alkali atom. And then you will see the transition among the energy levels and corresponding spectral lines one should see. So, in this case also this what should be the energy levels? Okay. So, spacing should be smaller and smaller when you are going towards higher. Okay. When you are going towards higher. Okay. I think this I should. Okay. So, in sodium there are 11 electrons. So, this outer electron, so transition as I told, these spectral lines will get due to the outer electron. So, this outer electron is generally it is at n equal to 3. Okay. So, whatever at n equal to 1 and n equal to 2 they are inner electron, it will not participate in transition. So, n equal to 3. So, there this outer electron is staying there, and then that can go at higher energy level, n equal to 4, n equal to 5, n equal to 6. So, it is a similarity from the similarity of hydrogen energy level. So, one can draw. Okay. So, one should get spectral lines, one should get spectral that series limit, one should get defined series, like another series could be this. Okay. So, that way defined series, and in alkali spectra that series was observed. There are mainly 4 series was observed. It is called I think principal series. Here I can write principal series, and then its other series is called, I think that is yeah. Yes, principal series, sharp series, then diffuse series, and then fundamental series. Okay. So, like Lyman series, Balmer series, etc. Here also this kind of series, similar type of series was observed. So, but unfortunately the wavelength of each series, okay, using this model, this term, the value whatever this term from Bohr model, whatever the value is giving. So, it is there is no, it cannot explain, it cannot give the correct value of the wavelength or frequency of this series, okay, spectral lines of the series. And it is not only it can give, it is there is a huge difference, So, so there is a huge difference, and it has to be it has to be look towards the validity of this Bohr model for alkali atom. Okay. So, later on we will see what is the source of this series, and we will see this this is not the source, this is not this model whatever it is giving, it is not enough to explain this series, to get the exact wavelength of the spectral lines of this series. So, as per this one, whatever the wavelength, or as per this one, so this number in principle whatever this transition I showed, later on we will see at n equal to 3 transition from this other n equal to 4, 5, 6. So, this each line basically, each line is not a single line, each line will have again is composed of many lines, and this each line is composed of many lines, but it is not giving a series. So, it is the mixture of this all 4, all others, all this. Okay. But basically with these 4 lines, each lines is composed of many lines, spectral lines. Okay. And they are distributed, they are arranged in a such way, they build up this 4 series. Okay. So, we will get from these 4 lines whatever this from Bohr model we are getting. So, these series are not visible, or this may exist, but it is not prominent one. So, here also again the same things happening. It is not a single line, it is not a 4 lines, these 4 lines have many lines, each line is having many lines. So, but ultimately from Bohr model whatever these 4 lines we are getting, these 4 lines will give this 4 series, each line will not give one series, but as I told this we will see that mixture of this 4, okay, they will form this different series. Okay. So, one thing is clear, whatever from Bohr model, whatever the spectral lines we are getting, but actually each line is composed of many lines, spectral lines. Okay. So, this indicates that, and that spectral lines actually we are getting due to the discreteness of the energy level, and discreteness of the energy level we got due to the quantum condition, right. So, one quantum condition taken in Bohr, that is the angular momentum is quantized, and that is basically lead to the quantization of the energy level. Okay. So, as if transition between 2 energy level gives the spectral line. So, as if it looks that this each energy level whatever from Bohr model we got, this level is not a single energy level, it is composed of many levels, many energy levels. Okay. Their separation may be small, or they may have same energy, but there are many. So, if energy levels are composed of many levels, few levels or many levels, and then there is a possibility to get many spectral lines. So, that is the indication. It is failure of Bohr model, but it giving indication that there are more discreteness among this energy level in each energy level. Okay. It is not a single energy level. So, we need more quantization, we need more quantum number. Okay. So, that is the from the failure of Bohr model we could learn something, and in that direction people started to think how more quantization is possible. So, that we will discuss now. So, what we have learned? So, more spectral lines, so more energy level, we need more quantum number or quantization. Okay. So, one thing, so people started to think, and I think Wilson and this Wilson and Sommerfeld, they yes. Yes, Wilson and Sommerfeld in 1916, Wilson and Sommerfeld they started to think on this issue, and they try to understand the quantization process. So, first quantization was given by Planck's quantization. So, sometimes I write S, sometimes I write Z, in American English and UK English. So, but you can write either S or Z. So, Planck's quantization. Okay, what was that? Planck's quantization was that energy of a oscillator is quantized. Energy of an oscillator is quantized, right, in black body radiation. So, electron or this atom on the surface of the black body cavity. So, it oscillates, and due to this oscillation it radiates. Okay. So, this energy of the oscillator is quantized. So, that is the Planck's quantization, right. So, energy of the oscillator is quantized. And then second quantization was the Bohr quantization. What is that? Bohr quantization was that the electron will rotate in a or revolve in a circular orbit, but it cannot choose any orbit. The orbit radius will be such that the angular momentum will be quantized. Angular momentum of that electron revolving in a circle is quantized. Okay. So, here Bohr considered this quantization in H cross, L equal to n H cross. You see, this quantization is completely different in nature. One is energy quantized, another is angular momentum is quantized, and energy of an oscillator is quantized. Okay. So, then Wilson and Sommerfeld, they started to think that what should be the what are the parameters, what are the things can be quantized, and they found the general rule. They found the general rule that any system, okay, to describe that system we need coordinate. Any system, to describe that system we need coordinate. Okay. So, if coordinate is a periodic function of time, if coordinate is a periodic function of time for that system, okay, so that parameter has to be quantized. That parameter has to be quantized. Okay. So, that is the general, it is neither oscillator nor angular momentum, it can be any system. To describe that system we need coordinate, right. To describe the system we need coordinate, and all coordinate may not be the periodic function of time. Those parameters which will be the periodic function of time, that parameter can be quantized. So, that was the quantization rule set up by Wilson and Sommerfeld. So, based on that, so this that means, so they gave this general action, it is called action integral. So, to describe a system we need say momentum and space coordinate, say p q, to generalized coordinate. So, p momentum, generalized coordinate dq, pq, and then dq, it is a integration, closed integration, it will be n h, okay, n q h, okay, n q h. So, that was the general quantization given by Wilson and Sommerfeld. So, if so that you see, now just consider the harmonic oscillator, simple harmonic oscillator. Okay. So, it is what is its energy? E equal to p square by 2m plus half k x square. You remember spring mass system is oscillating. Okay. This k is the some constant, spring constant. So, this is the potential energy, this is the kinetic energy. Okay. So, this we can write p square by 2m e divided by e, 2m e plus x square divided by 2e by k. I can write equal to 1, equal to 1, right. So, this I can write it is like this. So, it is the p q. So, here q I have taken x, so this I will write p x, okay, p q, q I have taken x and p is momentum p x. So, this I can write p x, this is square divided by say b square plus x square divided by a square equal to 1. Okay. So, this is the equation of ellipse, right. It is the equation of ellipse, okay, but in phase space, momentum and space coordinate x, okay. It is called phase space. So, here I can, so its motion in a phase space is I think I have to draw ellipse, so it looks circle. Okay. So, this is p x, this axis p x, this is x axis. Okay. So, p x, these two coordinate, okay, it is basically each point coordinate is basically to fix the position of the particle, right. So, in phase space using p x and this x, we can fix the position of the in this case of the motion of the oscillator. Okay. So, from here, so this the elliptical, as if elliptical motion is phase space of this oscillator, and from here you can get this A equal to comparing this A equal to what you are getting, A equal to square root of 2 E by k, and B equal to you are getting square root of 2 m E. Okay. So, here this is A and this is B. Okay. So, now integral of this, if the integral of this p x dx, okay, what will be the integration value, integrating value for a one complete rotation? It is nothing but the area of this ellipse, right. So, area of this ellipse is basically pi a b, pi a b. So, this integration is basically pi a b. So, this directly without considering any quantization, so the just I have started from the simple harmonic oscillator, I wrote the energy, and from here I describe it, nothing to do with the quantization. Okay. Now, if I consider quantization, so in this case I can, so two parameters p x and x, right, it is describing this system oscillator. Okay. So, they are periodic in nature, p x, because this x value and p x value, okay, it's it can change. Okay. Here is as a function of time it is changing, okay, and it is periodic in nature. So, I can apply quantization for that. So, here if I start from quantization that action integral. So, p q means in our case p theta, not p theta, p x, and then this is dx, okay, equal to n q h. Okay. Now, from here what you are getting, p x dx, this integration, if you take this integration, because this I cannot write if I do not consider the if I do not consider the system which has this elliptical path, means periodic nature. Okay. So, I have taken this one, system is like this, then I can apply quantization, this quantization rule, and I can write this. So, p x dx is basically pi a b, pi a b, pi a b. Okay. So, what I am getting? I am getting pi a b equal to n, I think I will write n x h, okay, So, then pi, what is A and what is B? A into B, what I am getting? A into B, I will get 2e square root of m by k. I will get 2e square root of m by k, square root of m by k, or 1 by k by m. Okay. So, k by m, you know, spin mass system is nothing but k by m, square root of k by m is omega. Okay. So, square root of k by m is omega, and omega equal to 2 pi omega equal to 2 pi nu frequency, 2 pi nu. Okay. So, I can write here 2e, this k by m is omega 2 pi nu. So, it is a square root, I can write here just square root this way. So, 1 by this. So, 1 by 2 pi nu. So, this I can write, replace this one, 1 by 2 pi nu, and this equal to n x h. So, just write n h. Okay. You can write n x or n, fine. So, from here you can see pi is going and 2 is going, and I am getting n h equal to E by nu, n h equal to E by nu, E by nu. Okay. So, nu, from here what I am getting? E equal to n h nu. So, from here I am getting E equal to n h nu. What is this? This is exactly that Planck quantization. It is exactly that Planck quantization. Okay. Similarly, you can also, starting from this action integral quantization rule, if you take an electron rotating in an orbit, for that you need coordinate. What you need? You need coordinate r and theta, right. So, if it is circular orbit, then r is constant, but theta is a periodic function of time. Okay. So, to describe that one we need r theta, but r is constant if it is circular, and only theta is a periodic function of time. So, if you consider this electron whatever Bohr considered, and then if you proceed the similar way, okay, you can show from this starting using this action integral or quantization rule, you can show that you will get that this angular momentum is quantized. Okay. So, that is your homework. You can show easily. Just one example I have given, rest on just you can show this. So, whatever we have quantization, this is a general rule, and that rule is it can reproduce this. So, it is not only for this, it can, so it is a general rule for other system also one can use. So, that was the then Sommerfeld, that is called Sommerfeld model. Sommerfeld introduced the elliptical orbit for electrons. In atom, Bohr considered circular orbit, and Sommerfeld introduced, no, it is not the elliptical orbit, circular orbit, it should be elliptical orbit, and that is what planet also in planet, and in any central force which is 1 by r square, gravitational force, Coulomb force 1 by r square. Okay. So, in central force, okay, so there this orbit is generally the elliptical orbit. So, Sommerfeld introduced elliptical orbit, considered elliptical orbit, and so basically he introduced this concept in Bohr model, and then if it is elliptical orbit, then r theta 2 parameter, and both are variable with time, both are periodic function of time. Okay. So, we will have two coordinate. So, there will be two quantization, and we will get two parameter, two quantum numbers. Okay. So, that we will discuss in next class. I will stop here. Thank you.